Any two coplanar polygons of the same area are equidecomposable. This means that each can be cut into a finite number of pieces, which can then be reassembled to form the other. Of particular mathematical interest are the motions that relate corresponding pieces. We will examine the way in which each piece is moved from its place in one polygon to its place in the other. For instance, in Dudani's famous dissection of the square and the equilateral triangle, the motions are just translations and half-turns. Half-turns are 180-degree rotations. We'll start with a simple case. Two parallelograms of equal area having a side in common. Translating the parallelograms gives us a network of lines which determine the dissections. Now, the pieces of one parallelogram can be translated to form the other. In this case, translations are enough. We say that the two parallelograms are T-equivalent, T for translation. If one of the parallelograms is T-equivalent to some polygon, then we have two ways of dissecting this parallelogram. We superimpose the cuts of the two dissections and make corresponding cuts on the other two figures. This enables us to show that the polygon is T-equivalent to the second parallelogram. We use the fact that the product or succession of two translations is also a translation. In this case, T-equivalence is transitive. In the same way, we can prove that T-equivalence is always transitive. Now let's consider two parallelograms of equal area anywhere in the plane. Intersecting strips determined by the two given parallelograms form a parallelogram, a diagonal of which provides the clue for the dissections. By translations alone, we obtain two parallelograms still equal in area and with a side in common. After superimposing the cuts where the parallelograms overlap, we can proceed as before, obtaining the rest of the dissection. These two parallelograms are T-equivalent. So by the transitivity of T-equivalence, the two original parallelograms are T-equivalent. This shows that a parallelogram is always T-equivalent to another parallelogram of equal area. A parallelogram is T-equivalent to a polygon only if the polygon has the following property. When the boundary is oriented, the algebraic sum of the side lengths in each direction is 0. A triangle doesn't have this property, so no triangle is T-equivalent to a parallelogram. But by a single cut, followed by a half-turn, the triangle can be converted into a parallelogram, which is T-equivalent to any other parallelogram of equal area. A half-turn followed by a translation is just another half-turn. So the pieces of the triangle have been reassembled to form the parallelogram by half-turns and translations. We say that the two figures are TH equivalent, T for translation and H for half-turn. These three figures all have the same area. The triangle can be cut into pieces which by translations and half-turns form the trapezoid. The triangle and the trapezoid are TH equivalent. The trapezoid and the parallelogram are also TH equivalent. By superimposing the cuts of both dissections of the trapezoid and making corresponding cuts on the other figures, the pieces of any one figure can be reassembled to form either of the others, using only translations and half-turns. Since products of these motions yield only translations and half-turns, corresponding pieces of the triangle and the parallelogram are related by translations and half-turns alone. The triangle and the parallelogram are TH equivalent. In fact, it can be proved in this same way that TH equivalence is transitive. So two polygons, TH equivalent to a third polygon, are TH equivalent to each other. We're now able to deal with any two coplanar polygons of equal area. Our argument uses a parallelogram of the same area. First, dissect one of the polygons into triangles. Then dissect the parallelogram into smaller parallelograms in such a way that there is a one-to-one correspondence between the smaller parallelograms and the triangles, corresponding pieces having equal area. Since their areas are equal, corresponding triangles and parallelograms are TH equivalent, so the complete polygon and the composite parallelogram are TH equivalent. Now, dissect the second polygon into triangles and proceed as before. Corresponding triangles and parallelograms are TH equivalent, so both polygons are TH equivalent to the parallelogram. By transitivity of TH equivalence, the two polygons are TH equivalent. Clearly, any two coplanar polygons of equal area can be dissected so that corresponding pieces are related by either a translation or a half-turn.